into part 2 here for section 11.10, dealing with Taylor and Maclaurin series. So let's find the Maclaurin series for sine of x and prove that it represents sine of x for all values of x. So the first thing we're going to do here is we're going to get a few derivatives. This is going to allow us to really see the pattern before we write out the series. So I'm just going to separate us off a little bit here, and we're just going to work in this space. So I don't know if I gave us enough room there. Go ahead and just use a box. You can make like a table or something if you want. So we have our function in question. That's sine of x. So the derivative is cosine of x. The second derivative, which is the derivative of cosine, right, is negative sine of x. The third derivative is negative cosine of x. And the fourth derivative brings us back to sine of x. All right, this one has kind of a recursive relationship where they keep repeating every 4, right? Every 4 derivatives we get back to what we started with. So if we're looking at the Maclaurin series, this is where a equals 0. So we're going to have f of 0, that's sine of 0, which is 0. F prime of 0, so cosine of 0, that's 1. F double prime of 0, so that's negative sine of 0, which is 0. F triple prime of 0 is negative 1. And the fourth derivative at 0 is 0. So you can see the pattern here will repeat. It just goes 0, 1, 0, negative 1, 0, 1, etc., etc. So when we set up the Maclaurin series, we're going to have, so f of 0 plus f prime of 0 over 1 factorial times x, right? Because a is 0, so it's not x minus a anymore. It's just x for the Maclaurin series. Plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, etc., etc. Okay, so then if we write that out here, so with the values we know, right, this repeating pattern, that's going to be just 0 for that first one, plus 1 times x, so that's going to be plus x, plus 0 for the square. And so basically, if you can see what's going to happen here, the 0 power, the 2 power, the 4th power, 6th, 8th, 10th, etc., all the even powers on this thing are going to have coefficients of 0 because of this pattern over here. So we're only going to be looking at the odd ones, and the odd ones are going to alternate positive and negative, back and forth, back and forth. Okay, so we're going to get minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc., okay, which is the sum n going from 0 to infinity of negative 1 to the n of x to the 2n plus 1 power over 2n plus 1 factorial. And that is the Maclaurin series for sine of x. So this is how we can represent sine of x using a Maclaurin series. So now we can go ahead and prove that this Maclaurin series represents sine of x for all values of x. Okay, and we're going to do that similarly to what we did for e to the x. So let me go ahead and just type what I can here. So since the n plus 1th derivative, so I'll put that derivative in there in just a second, of x, since the n plus 1th derivative of x is going to be either plus or minus sine of x, or plus or minus cosine of x. Let me pause and fill this in here. So the n plus 1th derivative is plus or minus sine or plus or minus cosine, right? Because every derivative that we have here is either going to be a sine, a cosine, or a negative sine or a negative cosine. So since every derivative here is going to be either a sine or a cosine, we know that the absolute value of that is going to be less than or equal to 1 for all x. Okay, so the absolute value of f of x, is going to be less than or equal to 1 for all x. All right, and that's again because sine and cosine are bounded, right, between -1 and 1 at all times. So the absolute value of that function, because it's sine or cosine, must always be less than or equal to 1. Okay, so since that function is bounded by 1, let's go ahead and make m equal to 1 in Taylor's inequality. All right. So in the inequality, so remember this from a little bit ago, we have the absolute value of the remainder is less than or equal to m over n plus 1 factorial times absolute value of x to the n plus 1. So when m is 1, we just get absolute value of x to the n plus 1 over n plus 1 factorial. And if you remember from one of the properties we talked about earlier, that helpful fact back up at the top of the page, we know that as n goes towards infinity, this heads towards 0. All right, so we have that the absolute value of the remainder heads to 0. So the remainder itself must go to 0, or excuse me, the absolute value goes to 0 by the squeeze theorem, like we saw in the proof above. Thus, the remainder itself goes to 0. And if the remainder goes to 0 as n goes to infinity, then that means that the Maclaurin series must be equal to the value of sine. So sine of x is equal to the sum of its Maclaurin series. So you can see finding the series, just a matter of observing those derivatives, those patterns, to get the coefficients. And then that proof is very similar to the one we just did above. Okay, so using that Taylor's inequality and then applying the squeeze theorem to get that it is equal. Okay. Next up, let's find the Maclaurin series for cosine of x. Now, we could use the same method as before, but because we now know the Maclaurin series for sine of x, we can just differentiate that series for sine of x, and that'll give us cosine, right? Because cosine is the derivative of sine, and that's going to make our work so much easier for this one. So we are just going to differentiate. So we have cosine of x, that is the derivative of sine of x. So the Maclaurin series for cosine must be the derivative of the Maclaurin series for sine, which is, so the series for sine is x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, etc. Okay, and that is 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial, etc. So we have 1 minus, notice what happens here, I can cancel the 3 with the 3 in the 3 factorial, right? So this is 3 times 2 times 1, so I'm going to cancel with that one, and I'm left with x squared over 2 factorial. So x squared over 2 factorial. The same thing happens to the next one. We get x to the 4th over 4 factorial minus x to the 6th over 6 factorial, etc. And that pattern repeats, so we get the sum with n going from 0 to infinity of negative 1 to the n of x to the 2n over 2n factorial. Okay. So you notice that the sine basically takes all of the odd powers, the cosine takes all of the even powers. So you can see an interesting relationship between the two of them. So then if we're talking about convergence, so since the Maclaurin series for sine of x converged for all x, the differentiated series for cosine of x also converges for all x. Alright, so there we have our Maclaurin series for cosine of x, and it's convergent for all real numbers. So here we have a table. It just gives us a few of the important Maclaurin series which we've been looking at. So we have, right, 1 over 1 minus x. We were using that a lot in the last section to determine power series expansions. And then we are looking a lot at e today and sine and cosine. Those are the ones that we've been talking about in this section particularly. So it gives their Maclaurin series and their radii of convergence. Okay, so with e, sine, and cosine all having a radius of convergence of infinity. Now, one major use of Taylor series is that the reason that we tie it into this discussion in Calculus 2 is to be able to integrate. So we can actually use Taylor and Maclaurin series to integrate functions that we couldn't work with previously. So we looked at a lot of techniques of integration back in Chapter 7 in particular, but this opens up a whole new world of being able to integrate functions that we didn't have techniques for before, because Taylor series give us polynomials, and we can work with those polynomials a lot more easily than we could with some of these more complicated functions. So a lot of like the more complicated formulas and like the table of integrals, a lot of those formulas come from these series. And in fact, infinite series and Taylor series like this is what your calculator does. So this next example, we're going to evaluate the integral of e to the negative x squared dx as an infinite series and look at its error. This is what your calculator does. Your calculator is computing an infinite series for e to the negative x squared, and it's evaluating it like we're going to. And then we're going to determine how big our error is, and the calculator also does that. It makes sure that it has as little error as possible. That's what we would call like rounding. The calculator rounds because it doesn't do it forever. But it's really interesting to get kind of a feel for what your technology is actually doing when it's just chugging out a number for you. So let's look at this example here. So to find the Maclaurin series for e to the negative x squared, we're just going to use the Maclaurin series for e to the x and then just replace in negative x squared instead. Okay, so find the Maclaurin series for e to the negative x squared. I'll put that in there in just a second. By replacing the negative x squared into the series for x. There we go. Okay, so to get the Maclaurin series, instead of starting from scratch like we did before, just use ones that we already know, and then that's going to make our jobs even easier. So we have e to the negative x squared equals the sum, n going from 0 to infinity, of negative x squared to the n over n factorial. This, if we break this apart just a little bit, make it easier to work with, this gives us negative 1 to the n times x to the 2n over n factorial, which, if we write out a few terms of this, looks like 1 minus x squared over 1 factorial plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, etc. Okay, so notice it's alternating positive, negative. The power in the numerator is always even, and the denominator is just counting up, right, as n increases. So once we have this series, we can go ahead and integrate. Integrate both sides of this, and the value on the left would be equal to the value on the right. So we're going to get the integral of e to the negative x squared dx equals the integral, and we can integrate term by term here, so we have 1 minus x squared over 1 factorial plus x to the 4th over 2 factorial, etc. dx. Okay, so that's going to be c, arbitrary constant, plus x minus x cubed over 3 times 1 factorial plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial, etc. Okay, and then plus, let me go ahead and just add that arbitrary term in there. So the general form of the series would then look like negative 1 to the n times x to the 2n plus 1, right? Adding 1 to the power, and then dividing by that same number, so 2n plus 1 times n factorial, and then etc., etc., etc. Okay, so just showing the general term for that series. So in terms of convergence, so we can say this series is just as convergent as e to the x was. So this series converges for all x because the original series did. Okay. So then part B, now that we have this general formula for the integral of e to the negative x squared as an infinite series, we can use this to evaluate the definite integral, try to get area under the curve. So let's go ahead and do that. So we have the integral, separate this off here. We have the integral from 0 to 1 of e to the negative x squared dx equals, right, x minus x cubed over 3 times 1 factorial plus x to the 5th over 5 times 2 factorial, etc. And I'll go ahead, I'll throw another one in there. X to the 9th over 9 times 4 factorial. Evaluated from 0 to 1. So this is going to be, when you evaluate all the zeros, they're just going to turn to 0. So that's going to be 1 minus 1/3 plus 1 over 10 minus 1 over 42 plus 1 over 216 minus etc., etc. Okay. Now, obviously this series goes on forever, so we couldn't list off every single term. We shouldn't even try. But we can go ahead and just approximate this by cutting it off at a certain point. And we'll just cut it off here at that term x to the 9th. So this is approximately equal to 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 216. Okay, so it's approximately equal to that. And that value is approximately 0.7475. Okay, so that is the approximate value for the area under the curve, e to the negative x squared, from 0 to 1. Now, how good is this approximation? Well, we could use, if you go refer back to the previous sections, we can look at the alternating series evaluation theorem. So this shows the error involved is less than is less than 1 over 11 times 5 factorial, which is 1 over 1320, which is less than 0.001, okay, which is what was required of us. Right? So evaluate within an error of 0.001, and we did that. Okay? So depending on how close you needed to get with this calculation, that could be sufficient, or maybe not. If you needed to be even closer, then you just go further along in the series, right? Add a few more terms on there. So, All right, and then we have one more example down here, evaluating a limit. So for this limit, if you try to plug in 0, use direct substitution, you'll notice that this one is indeterminate. So we could use L'Hopital's rule on this, but we can also use infinite series on this as well. So we have the limit as x approaches 0 of e to the x minus 1 minus x over x squared. If we write out the expansion for e to the x, then we're going to get 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc. minus 1 minus x all over x squared. We're going to get a little bit of cancellation. We have a 1 minus 1. This is just x minus x. So what we have left is the limit of x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. all over x squared. You can split this up, right, into a bunch of separate fractions, right, putting them all over x squared, and then cancel as many terms as you can. So that's going to leave us with 1/2 plus, we'll have a 1 factor of x left over 3 factorial plus x squared over 4 factorial, etc. And now, as x goes to 0, that one goes to 0, that one goes to 0, and every term after that is going to go to 0 because it still has an x in it. So the value of this limit is 1/2. Okay, so, and not to necessarily say that this would be easier or harder than using like L'Hopital's rule, but just to show you that these series do have way more uses than even just what we're covering in our brief time here in class. There's a lot more to these. They have a lot of different uses, so including even just finding limits. So we can also, you can see down here, we can also multiply and divide power series as we would with polynomials, just going term by term, but we're not, for the sake of time, we're not going to do that in our class. But just know that that is something that we could do as well. We also have that option of multiplication and division of power series. So that brings us to the end of section 11.10. So only one more section to go, pretty short one, thankfully. Just finishing up our conversation on Taylor and Maclaurin series. So I'll see you guys back for that one.